So let's talk about optimization. What does the word optimization mean?
Making it the best it can possibly be.
Okay, trying to get something the best it can be. In problem solving, we're trying to find the best possible solution for a problem. One thing that we have to clarify, though, as we're doing these, is we need to define what best means in our given situation. Okay? Sometimes that'll mean the most of something, like we want to make a container that will contain the most volume possible, or we want to make our profits the most, or our revenue the most. However, in another instance, it might be the least. The best solution might be the least amount of something. If we have the least amount of expenses, or we're able to produce something with the least amount of materials, that sort of thing. So you really need to make sure that when you're talking about an optimization problem, that you are defining, at least in your head, what best is. So you know what you're looking for. Now, I want to just kind of run through a quick method and then model this method here for you. It's just a basic problem-solving method that you may have, not this exact one, but you may have used something similar to it in the past as far as the beginning stages, but I want to apply it directly to these optimization problems here, okay? Let's try to focus, okay? First thing first, draw yourself a picture. Most of these, you'll be able to have some sort of a picture, okay? Obviously, you might be dealing with things where we're optimizing something that's a rate of change for something that's not really tangible. But if it's tangible, if it's something that you can visualize, draw yourself a picture and help yourself understand the situation, okay? Secondly, and this is really the most important, this is where the vast majority of your work comes in. Because after this, you're just taking a derivative, finding critical points, doing all the stuff we've been doing. All right, this right here, though, is kind of the key step of this whole section. That is constructing a formula with the variable to be optimized as the subject. Okay? So there's two parts to this. First of all, if I'm trying to optimize area, then I'm going to write a formula or a function where my function equals the area. All right? If I'm trying to maximize my profit, I'm going to make my whatever formula I'm coming up with equal the profit. All right? I want to make the thing that I'm trying to optimize the thing that my function equals. Okay? The second part of this is that we need to make sure that it's in terms of one variable. Okay? A number of the problems you're going to be dealing with are problems where there may be more than one variable initially. And then you have to try to get one of those variables in terms of the other, so that you have your function in terms of just one variable. So, like I said, this is going to be the part where we have the biggest amount of work. The third part of this step also is the domain. Okay? What domain restrictions are there? Okay? Understanding this is really important because this gives you the range of possibilities for your answer. Okay? It is possible that the maximum on the entire function is not the maximum within the range of possible solutions. Okay? So you've got to figure out what is physically possible based on our situation, and then set up your domain for that. Okay? So that's where a lot of the work is coming in. Thirdly, find the derivative and the values that make the derivative 0. Okay? You're finding those critical values. Okay, finding those critical values. Because we know that that's where our max and min points usually lie. Okay, or at those critical values. And then fourth, here's where all this stuff that we've been doing, proving that something's a max or a min point, doing sign diagrams, all of that kind of thing, this is where that all comes into play in these problems. Except there's an additional part to this. The max or the min for any problem is going to occur either at one of these critical values or at an endpoint, okay? And what are we talking about the endpoint? The endpoint could be where at the end of where our domain is restricted to, okay? So, for example, let me give you an example here. Let's say we had this function that looked like this, okay? If we were finding a local max or min point, obviously the max would be right here. However, if our range of possibilities went from here all the way over to here, the endpoint of this range is actually a value that's higher than this local max point was. Okay? So this would actually be the best solution. All right? So, don't just jump to the conclusion that the critical value automatically, if it's a max, it's going to give you the highest value. This is why, again, determining that domain is so important. Okay? Now, you should, if you've got a critical value, you should actually prove that that is a max point or a min point, whichever you want it to be. Okay? The other thing about this is, and again, this goes back to defining your domain carefully, it is possible that the critical value itself is not the best possible solution, but that it's really, really close to it. It all depends on the situation. You got to define best for each situation. Okay. What could happen, however, is let's say you're in a situation like we were looking at that sales model, or production model, I should say. We were producing X number of items per day. Let's say the optimal solution, our critical value, was at like 120.6. Well, obviously, you can't make 6/10 of an item. So what you would do then, though, is test 120 and 121 along with the endpoints of your range, and that you could then get a max from. Okay, if you were trying to get the maximum production or minimize costs, it would be, you'd get the integer closest. So you need to identify right here when you're doing your domain whether or not your answers have to be integers or if they can be fractions as well. Okay? So,
how do you, I've never seen a sign, have we ever seen a sign diagram test where the derivative is undefined?
Yeah. Remember, we did some with like rational. Like you had x plus 4, let's say your derivative was x plus 4, let's do the original function here. We'll keep it simple. X squared minus 9. Here's our original function. Okay? You have x plus 4 times x squared minus 9 over x plus 4. That's our original function. Okay? Obviously, the domain for this is that x can't be negative 4.
Yeah.
So on your sign diagram, you would put negative 4 before you even bothered taking an integral.
Yeah.
Or a derivative, sorry. Then, when you went to do f prime of x, you'd reduce it first and then get the derivative of this, that's 2x. So the critical value is at 0. Okay? So you would include anything that was eliminated from the domain.
Okay.
Yeah. Because it's in this case, it's a hole. It's a hole here. If it were an asymptote, same thing. Okay? But you would do the sign diagram for all three regions here. Now, finally, make sure that you clearly answer the question. Don't just do a whole bunch of calculus and have a number at the end and just leave it up to whoever happens to be reading it to figure out what your answer is. Make sure that you clearly explain what the solution is to your problem. Okay? So, let's work through this whole process here with the following problem. Okay? Here we have a 4-liter container, and it has to have a square base, vertical sides, and an open top. Okay, so a couple things here. It has to contain 4 liters exactly. It has to have a square base, vertical sides, which means this is a square pyramid, a square prism here, and an open top. And it says, find the most economical shape which minimizes the surface area of material needed. Okay? So the most economical shape. In other words, like it describes here, we want to minimize the surface area. That's going to be the most economical because to build this thing, the less surface area we have, the less material we have to use to make it. Okay? So the first thing that we're going to do is draw ourselves a diagram. We see that it has a square base. Okay, so I'm going to draw a square base, and I'm going to indicate it. I'm going to indicate that this is a square base by labeling the sides of it both x. Okay, and then it has vertical sides. All right, so this is going to be a prism shape. So I'm going to go this. Okay, it doesn't have to be a perfect drawing, but there we go. Okay, so there's our prism. And I don't know how tall this thing is, but do be careful you don't assume that it's exactly the same height as it is around the base. Okay, so I'm going to actually label this H. Okay? So I have a diagram. It's labeled clearly. And now I know what I'm dealing with, okay? There we go. So now I know what I'm dealing with. The other thing that I want to figure out is what my domain would be, okay? I'm gonna put everything in terms of x, but what are the limitations here?
It could be 0.
Huh?
It can't be 0.
Can't be 0. What else? It can't be negative, okay? So we would say that x has to be greater than 0. Right? Now, this does not have, theoretically, well, 0 is an endpoint. We're going to approach 0. There's really no cap on this theoretically. Okay, theoretically, we could make something that was, 2,000 miles wide and 2,000 miles long as we made it just tall enough, could still contain 4 liters. All right? It wouldn't be very useful, but theoretically it could do that. All right? So, we have no end on the top as far as how big x can be. All right? So now it comes to the point where we need to figure out a formula for the variable that we want to optimize. Okay? We already got the domain here. So what is our formula going to equal? What are we trying to optimize here?
We're trying to optimize the volume.
No? Surface area. What's our volume going to equal?
4 liters.
4 liters, okay? Our volume equals 4 liters. Okay, we want our surface area, and I'm gonna make our surface area be in terms of x. Okay? Now right now though we have the x and the h. However, this is where this other piece of information comes into play, because I told you we have more than one variable, so we need to write h in terms of x. All right? So let's think about this. 4,000 liters, I have here a little conversion. A liter is 1,000 milliliters, and 1 milliliter is 1 cubic centimeter. Okay? So how many cubic centimeters would be in 4 liters?
4,000.
Yeah, 4,000. Okay? So 4,000 cubic centimeters. Now, how do you find the volume of a prism? Yeah, base times width times height. Okay, so x times h, right? So I know that 4,000 equals x squared times h. So that now tells me what h equals. What does h equal?
4,000 over x squared.
Yeah, there we go. 4,000 over x squared. Okay? Now, it's possible you could try maybe making a right triangle in here and finding this, and then making another right triangle with that diagonal. But we actually don't have enough information trying to do it that way to get h expressed in terms of just x. All right? So there may be a variety of different ways that you could do this in some cases. In this case, this is the only route we can take. Okay? So now, let's think about this. My surface area, I don't have a top, so I'm only going to include the bottom. So what's the area of the bottom?
X squared.
X squared plus all 4 of the sides. The 4 sides are rectangles, and it's x times h.
So 4xh.
So 4xh, but what is h?
4,000 over x
4,000 over x squared.
squared.
So if I plug in a 4,000 over x squared times 4x, what does that give us? This times,
What? What are you talking about? Oh, that's the surface area. Oh.
what does that simplify to? Come on.
16,000 over 4 x
Over x cubed. 16,000 over x.
16,000 over x. This x will cancel out one of those two. All right? So 16,000 over x. Okay? So now we have our function. And the nice thing is that was the hardest part. Okay? That was the hardest part.
Okay, step 3, find the derivative and the critical values.
Okay.
So 2x.
All right, so yeah, we're finding the derivative and the critical values. So what is the derivative of s of x?
2x.
2x.
2x plus whatever.
This is 16,000 x to the negative 1, right?
Oh,
Yeah, so negative 16,000.
X to the negative second, good. So you could put it over x squared or whatever, it doesn't matter. Okay? So now, everyone see how we got the derivative here? Okay? So now we need the critical values. All right, we need the critical values. So where does this equal 0? Okay? One thing I could do is just add the 16,000 over x squared to both sides. So 2x would equal 16,000 over x squared. And what?
You divide by 2, multiply by x squared, take the cube root.
Yeah, okay. So that would be 8,000 equals x cubed, and then we take the cube root. Do you know what the cube root of 8,000 is?
2,000.
No.
Close, we're getting close. 20, there we go. 20.
20 and negative
No, not negative 20. This is cube root, it's not square root.
20 and
So that's 20, what's our unit of measure here?
cubic centimeters.
Well, this is just a length, so it would just be centimeters, right? This is just a length, so it'd be centimeters. And that's our only critical value. Okay? There's only one critical value in this equation. Now, this problem doesn't really have ends. Obviously, x can't be 0, but x can get really, really, really small. And x theoretically could go up to infinity. All right?
Neither of which help.
Now, if you look at our original function, it's an x squared. Okay? So there actually will only be one change in direction here, even though there's an asymptote at 0. Okay? But there's a way that we can prove, so we don't have endpoints. We don't have endpoints to change or to try. The points where the derivative is undefined are also where the original function's undefined, so we don't have any of those that we really need to, or that we can really try. So really we're just trying the critical value. So at 20, here's where we're going to do a sign diagram. Okay, we plug this into S prime. If I plug in 0, that's to the left, and what do I get? Oh, that's undefined. I don't want to plug in 0. Let's say I plug in 1.
Well, it's going to be pretty negative.
If I plug in 1, it's going to be, really, really negative. Okay? It's going to be 2 minus 16,000. All right? So I know it's negative. Let's say I plug in a negative value.
Shouldn't we just not bother with that because it's outside what it could be?
It is outside the realistic domain. So really all we're concerned with is this. But you will see that's because we have an asymptote approaching 0, and then it jumps and it's going to approach here, and then at 20 actually it's going to actually end up being a min point. Okay? And the reason why is because if I plugged in 21 or something else, I'm going to get a positive number. Okay? Let's say I plugged in 100. Okay? I'd have 200 minus 16,000 over 100 squared. Well, that's 1.6. So 200 minus 1.6 is positive. All right, so I know it's positive. Okay? So now we've tested it and we've proven that x equals 20 gives a min point. Okay? And actually this graph right here is what this thing would look like. Okay? Are there any questions up to this point? Because all we have left to do at this point is just to write our conclusion. Yeah?
So you took the critical value of 20 and plugged it into the original equation? Or the derivative?
The derivative to get our sign diagram and prove that this is a min point. I know it's a min because we go from decreasing to increasing. Okay.
And 0 was
So.
I don't understand why you use the gas can't be 0. So why is that on our sign diagram?
Well, remember on your sign diagrams, you put anything eliminated from the domain, okay? Because there's an asymptote, and it can affect your increasing or decreasing. So,
Why do we only fund them? So we only have to fund the max for a min.
yeah, depending on the problem. In this case, we want to minimize the surface area. So we want the one that gives us a min. It's possible you could have a min and a max, then you just have to pick the right one, okay? So, giving our final answer here, all right, our final answer says give the most economical shape. In other words, give the dimensions. How would we make this thing, okay? So we would make this dimensions, we could say dimensions of 20 centimeters by 20 centimeters by 10 centimeters.
Why 10?
Oh, sorry, I didn't do that. Because if you plug in 20, you'll get 400 when you square it, and 4,000 divided by 400, there's our height, is 10. Okay? Would give a minimum surface area of, and now you go back and you can plug it into your original function. 200 or 20 squared is 400. 16,000 divided by 20 is 800. So our minimum area, surface area is 1,200 square centimeters.
So why not keep it?
Okay?
Why not keep it? Oh, because it's surface area.
Yeah, it's surface area. There you go. Okay?
So when you get your x, you plug it back into the original function to get your.
You plugged it. This is why the diagram and writing stuff down as we go is important. We went back here to what we had said h was in terms of x. Remember we used that volume?
Yeah.
H was 4,000 over x squared. So since we wrote that down, it's easy to remember how to get h.